Hi. In this presentation, I will focus on a fairly new commercial type of biologically produced biosurfactants. They are called microbial biosurfactants. You will learn about some examples of already commercialized microbial biosurfactants, in addition to their opportunities, so advantages, and hurdles or disadvantages. And also I will give a strategy to overcome these hurdles. Microbial biosurfactants are produced by microorganisms through a process called fermentation. These microorganisms can be bacteria, yeasts, fungi. Fermentation is a biological process which occurs in a bioreactor and typically at low temperatures between 20 and 40 degrees Celsius. Just like humans, these microorganisms require certain components to grow on, such as proteins and carbon. So same as we eat meat and potatoes, they also need nitrogen and carbon, but also vitamins and salts. The process will typically take place in water and can occur anaerobically or aerobically. In the second case, of course, you will need to add oxygen to the reactor. These components will be used for the yeast to grow. So by growing, it will produce biomass. This microbial biomass will subsequently perform the biotransformation. So of the biomass substrates, So for example, the sugar and the oil into a biosurfactant. Besides the produced biosurfactants, also other compounds are generated in a fermentation, such as other metabolites and also CO2 and heat. In the end, you will thus have to separate the biosurfactant from the complex mixture in a process called downstream processing or easier purification. Microbial biosurfactants have some clear advantages. They can be produced from entirely renewable resources, so 100% biomass, likewise as the other biosurfactants. But additionally, the production can occur from waste and even side streams, which is more difficult for the chemical production routes. Microbial biosurfactants are also biodegradable. They have added value, such as some additional biological properties beside their typical surfactant action. They are also not ecotoxic, and last but not least, the production process happens at low temperatures in water without the use of toxic catalysts by a so-called biotransformation, which is thus a biological, clean production process. These advantages have resulted in the commercialization of a number of microbial biosurfactants, although in very small amounts, which can be seen here. As you can see, only a very small part of the biosurfactant market is actually represented by these so-called microbial biosurfactants. The commercialized microbial biosurfactants can in general be subdivided into three main groups: glycolipids, lipoproteins, and polymeric surfactants. Glycolipids are the group with the most commercial examples, so best known. Sophorolipids, so sophorose attached to a lipid, are produced by certain yeast species. They mainly find application in detergents and personal care applications due to the combination of their cleansing effects and their mild antimicrobial properties, for example against microorganisms causing armpits, odor or dandruff. The wild-type mixture has mild to no foaming properties. Rhamnolipids, so rhamnose added to a lipid, are a second well-known example of glycolipid biosurfactants. They are produced by bacteria and are mainly suggested for applications in agrochemicals and personal care products. They are a good foaming biosurfactant and also have antimicrobial and even L-acetyl properties. Rhamnolipids are currently put on the market by Evonik under the trade name Riance-1. Second group are lipoproteins, thus consisting of a protein coupled to a lipophilic molecule. Surfactin is a lipoprotein and it's a very potent surfactant. The commercialization in Europe is done by the company called Lipofabric. But the commercialization remains very low as the product is quite expensive, but this is also because the production process is not efficient enough yet. A last group of microbial biosurfactants are so-called polymeric biosurfactants, and I will give one example. Emulsan is one example, and these biosurfactants are actually mainly produced in very low scale for DIY purposes. For example, you want to generate your own cosmetic, you can then buy this natural polymeric biosurfactant as a natural emulsifier. Although several examples of microbial biosurfactants have thus already been commercialized, their market volumes remain small, as we saw before. This is because there are also some disadvantages associated with them. When we look at what the market demands, which I have represented in a schematic way in this slide, you can see that the market wants uniform products, so products only containing one compound, which are quite pure. The surfactants buyers also want a lot of variation to choose from to make new formulations. It's a little bit like an art, making a painting. And above all, the products have to be cheap. Now, surfactants are bulk products, especially the ones used for household and industrial cleaners, which I have showed you before. They are the major part of the surfactant market. And you can imagine that these types of products do not allow high costs of raw materials. Now, biosurfactants are not cheap. This is of course related to the economy of scale and the fact that the production processes have not been optimized yet. If you compare to petrochemistry, it has been around for more than 150 years, it has been thoroughly optimized. Now, only a limited amount of products are also actually already on the market, so there's not a big variety. And moreover, biosurfactants are produced as complex mixtures. So you can see in the schematic view that you produce a mixture of very similar molecules, and you might say, yeah, what do I care? If the mixture does the job, why bother? This is true. But because we are dealing with a biological production process, there can be variation in between batches. So today you might produce a product which foams well and has good antimicrobial properties, while next week you want to repeat the process, and actually the thing that comes out is something that doesn't foam and is not antimicrobial anymore. This is attributed to the changing ratios in the surfactant mixture, so of the different very similarly looking compounds. And this will be a no-go for companies, as companies want to guarantee product performance and stability to their customers. So to then summarize the situation for microbial biosurfactants on the right, as opposed to the market demands on the left, you can see that in contrast to what the market demands, complex mixtures are produced instead of uniform products, and often the purification processes have also not been thoroughly developed, and you will have mixtures that are not pure. Now, it might not be necessary to have high purity for commercialization, but to perform application research, you have to work with very pure samples. This is necessary to avoid that you're actually testing the properties or the effects of a contaminant inside the mixture instead of the properties of the biosurfactant. Moreover, a last downside, so only a limited amount of biosurfactants are currently on the market. And then last but not least, they are also a factor 10 to 100 more expensive than bulk surfactants. Now, this is an unwanted situation. And at the University of Ghent, at InBio, and the Biobase Europe pilot plant, we have defined a strategy to solve these issues. So by combining genetic engineering and process development and also scale-up, you can actually overcome the disadvantages currently blocking more widespread commercialization of microbial biosurfactants. For example, strain engineering, so the engineering of the bug of the microorganism that produces the biosurfactant, can enhance a more uniform biosurfactant, while it can also help in increasing variety. Process development, on the other hand, will help in generating pure products, but also more uniform ones. This strategy, where you keep these different processes going and keep iteration between them, is a so-called integrated bioprocess design approach. Thank you for your attention.